final speaker for the session in the day is Yusu Wang. She'll talk about geometric ideas for graph analysis and learning.
All right, thanks. Can online people hear me? Okay, so thank you all for staying to the last talk, but after this, we still have the poster session. So I'm Yusu Wang. So I'm going to talk about one type of very common structured data, graph type of data, okay? So I assume that I don't have to really motivate why we care about the graph data. It's very common across many scientific and engineering domains. And in recent years, I think that the animation is lost. Or I can go ahead just like this, but yeah. So now, for example, there are many data that we can model by either geometric graph or abstract graph. You can model, for example, by chemical compound with a geometric graph, or you can model social networks with a relational network. Okay. So now, very recently, the graph neural network has emerged as a very powerful modern way to perform graph optimization and learning, okay, and has already been applied to many applications, including, for example, predict the properties of molecules directly from the bond structure. Okay. But despite this tremendous development and also applications, we actually don't have a lot of theoretical understanding about the graph neural networks, and also we also know that there are quite a bit limitations. Okay, so now my background is I think it is lost. So yeah. I'll just go ahead with this. Now, my background is in geometric algorithm and applied topology. And in the past 2 years, I mean, we and my group has been interested in that how to use some of the geometric ideas and also algorithm idea, try to provide better theoretical tools to understand graph neural networks and also to design better graph learning architectures. Okay. All right. Sorry about this. This share. It's working finally. All right, yeah. Okay, but I think the animation loss, I apologize for that. I think once it goes through the Google Drive and mysteriously something disappears. All right, so so basically I want to tell you some of our recent attempts using geometric ideas to try to better understand graph neural networks. Okay, but I'm going to start with a very brief introduction of, it's not reacting. No, it's not reacting. Okay. Nope.
How did it work on yours? I don't know why it's not.
Okay, thank you. All right. But let me start with but before that, let me start with actually a brief introduction about one of the most popular type of graph neural networks, so-called method passing graph neural networks, MPNN. Okay. Now, in general, we are kind of all familiar with neural networks, which essentially is a way to model a function from one space to another space. Like in this case, I have a map from R3 to R2, okay? But the neural network provides a way to build the composition of learnable pieces of this function, okay? Where each neuron is a parameterized function, essentially, that can be trained and learned. Now, how you design the neural network really the architecture depends on the type of data that you're having. This is a simple map fully connected just from Euclidean space to Euclidean space. You have input a C image, then you can also try to leverage the locality information and have convolutional neural network architectures. Now, when you come to graph type of data, now this is more challenging because the input graph doesn't have to have the same size. Okay, and also, given the graph, there's no canonical order among the graph nodes. Okay, so whatever you're designing, they should be able to work on graphs of different size and whatever permutation of the input that you're giving. Okay, so the challenge, the key is that how can you design an architecture with the shareable parameters that can be generalized to graph of different size and properties. Now, it turned out that there are multiple ways to do so. So here's actually one very simple idea, but very powerful, the so-called message passing graph neural network. Essentially says, okay, let's just try to manipulate node features. Instead of take the graph as a whole, let's assume that the node feature, at each layer of the neural network, you try to find a map, learn a map, going from node feature of some dimension to another node feature. Okay, so, and each layer, you keep manipulating this node feature. Now, how does the graph structure come into picture? Well, when you update your node feature, you want to leverage your neighbor's features. Okay, in particular, at every state, every node will take the collection of its neighbors and then look at their node features and then perform a so-called aggregation, the aggregate function on top of that, and then further update this. So what you need is that this aggregate function now is working on a set. In fact, it's a multi-set because some of the elements can be the same. And you need this function to be permutation invariant. Okay, that's essentially the only requirement. Okay, and there are many ways to do so. Here's just one very simple example to show that here I just simply averaging my neighbor's feature and I perform a linear transformation followed by a learnable linear transformation followed by a ReLU. Okay, so that's just one way to realize this, this idea. Okay, all right. So now, a lot of the theoretical study about this message passing neural network actually ultimately connects it to something which is very classical, the so-called Weisweiler-Layman graph isomorphism test. Okay. So this is the graph isomorphism test, namely, you give me two graphs, I would tell you either that these two graphs are not isomorphic, or I tell you that I don't know, I'm not sure, I cannot tell. So you cannot tell all the pairs of non-isomorphic graphs apart, but it can tell most of them apart in the probabilistic sense. Okay, so it's a very simple test. What does it do? In fact, it does the following. Let's say that I give you two graphs G and H here, and I want to know whether they're the same or not, isomorphic or not. Okay, assume that your input graph also comes with some initial node feature, some simple things, say constant, or in this case, degree. So every node comes with a degree. In the first step, I just try to look at the distribution of this initial feature. Just look at the histogram of the degree distribution. I say, these two have the same distribution. In this case, you can see they have the same degree sequence. So at this moment, I cannot tell this graph apart. Okay? Then I say, if I cannot, let me, for every node, I update my feature by looking at collecting all the features of my neighbors, and I look at that as a multi-set. So at this point, if you look at the degree 3 node in G, its neighbor degree is 1, 1, 2, 3, the multi-set. Okay? While for the top node in H, its neighbors are 1, 2, 2, 3. So this multi-set of neighbors feature are no longer the same. So at this point, I can already tell these two graphs are not the same. But if I still fail, I continue. I continue to keep aggregating my neighbor's feature into a bigger and bigger multi-sets as my representation and look at distribution of that to tell. Okay, so after linear number of iterations, this is going to stabilize. And then if you cannot tell, you return saying, I cannot tell whether they're isomorphic or not. Okay, so a very simple procedure. Now, I hope that from the way that I described this, you actually see the resemblance of this WL test and the original message passing neural network, because in both cases, at every moment, each step, you are aggregating neighbors' information and representing them in some way. Okay, and this is perhaps then not surprising that you can actually make this more formal. So here I'm just stating a very informal theorem, which says that in terms of the ability of distinguishing graphs, message passing neural network essentially is as powerful as this WL test. Namely, if you give me two graphs that the WL test cannot tell them apart, then no message passing graph neural networks can tell them apart. Okay. On the other hand, you can also have a message passing neural network that can distinguish all the graphs that WL can distinguish. Okay. All right. So now I'm going to get into some of the new results. Let me. Oops. All right. So I mentioned that the message passing neural networks expressive power is tied to WL test, and this has a range of consequences. Okay, so for example, depends on what you put as the initial node feature. Okay, message passing neural network cannot differentiate deregular graphs, can decide simple quantities such as diameter, radius, existence of triangles or other type of cycles, and so on. Okay, it cannot account certain many of the induced subgraphs and so on. Another consequence is that from this perspective, if I want to study theoretical property of message passing neural networks, graph distance such as graph edit distance is perhaps too refined, because graph edit distance will be able to tell non-isomorphic graphs apart, while we know that the message passing neural network cannot. So it's too refined to be used as a way to study, to put as a metric structure on the space of graphs to study properties of MPNN. Okay. So the question we're asking is that, what is the suitable pseudo-metric structure on the space of graphs that is compatible with MPNN, that's better for the theoretical understanding of MPNN, okay? And this would be useful for us to provide a way to study questions such as stability, universal approximation, and hopefully generalization, sample complexity, and so on, okay? On the other hand, note that just have a computable and a discriminative graph distance itself is also very interesting, because typical graph distance, such as graph edit distance, unfortunately, these are all very hard to compute. So graph edit distance is going to be hard to approximate with a constant factor, even for trees. Okay, so can we have something that is more computable and practical as well? Okay. All right, so in a joint work with, I think, Sam and my student Sam Chen and Zheng Chao, postdoc Zheng Chao Wan are both there, and also collaborator Liman Mimoli, we essentially kind of view the graph as certain type of Markov models. Okay, this itself is not new, viewing graph as a Markov model, but we're using this now for the distance, for the matching purposes. Okay, and we use the WL test itself, this procedure itself, to inspire us to obtain a distance, and which I'm going to give you the intuition in a minute. But this WL distance that we obtain is compatible with WL test, namely its kernel set are exactly those graphs that WL test cannot tell apart. And it's also, we argue, this is the right metric for you to study theoretical property of MPNN. In fact, we also obtain a universal approximation and also stability analysis of MPNN for functions defined on space of graphs where that continuity, the topology of the space of graphs is induced by this WL distance, okay? And so intuitively, what's happening, so this is just a very high level idea. What happens here is that, now remember that in the WL test, we're just looking at the treating node feature essentially as multi-sets of my neighbor's feature and then keep accumulate. Okay, this multi-set itself is not good from a metrics perspective. So you want to somehow metrize this, make this into a metric. Okay, so intuitively, we're going to use measure over certain metric space to replace this multi-set. And then we're going to use the push forward of measures essentially to replace this aggregation operations in the WL test. Okay, and since we're handling measures now, we use optimal transport as a way to compare those measures. So this is just a very high level idea, but in the end, it turned out the resulting distance has very nice properties. very nice theoretical properties. Okay. In a very recent work with Zheng Zhao Wan and also student Tristan sitting over there, we also, because now we're viewing graph as a Markov model, there's already distance developed for comparing Markov models. Okay. It turns out that we can actually have a unified framework that incorporates both our WL distance and another so-called optimal coupling distance for Markov models. And the byproduct of this is that this gives us a variance of this WL distance that can be differentiated. Okay, the implication is that now I could actually incorporate that into a loss function because we can now differentiate this distance now. Okay, the original optimal transport, in general, if you use graph edit distance, it's not very clear that how we can differentiate such a distance. Okay. Let me just point out that we already implement this, and if you need the code of, oops, I do need to thank them, but anyway, it's probably a hint that I should stop now. I'm not sure what is going on with this. This is really mysterious, very persistent, I think. Do we know what's going on? Anyway, so so here's an example where you are using optimization to find the mean of a bunch of noisy circle graphs with a random Erdős-Renyi type of noise. We model that as optimization function, and because now we can differentiate the distance, you can compute the mean of such noisy circle. Currently, we're using this as part of a reconstruction loss for generative models for netlist eclipse as applications. So let me just very briefly mention the other line of work, which is that, but can we use a theoretical understanding to help us to design better graph learning architecture? Okay. One of the issues with this method passing neural network is actually, it turned out it's not very effective at capturing long-range interactions in graph. Okay, and so in general, when we talk about modern days, we'll hear about deep learning. But if you look at the graph neural networks, usually they're very shallow, only 3 to 5 layers. Once the number of layers become increased, you have a range of issues, including the so-called over-smoothing issue, essentially related to graph signal processing, and over-squashing issue. Okay, the over-squashing intuitively refers to that as you are growing as the number of steps increase, you have to aggregate exponentially larger regions information into a fixed size feature. And it also turned out that the different type of graph structure, some of them suffer from this over-squashing more than others. Okay, so recently there has been some attempt to try to understand what is causing this over-squashing from a graph structure perspective. For example, it has been related locally related to the so-called Foreman graph curvature, and also empirically is also related to the spectral gap of the graph structure. Okay. So in one of the recent work, we showed that actually you can relate this over-squashing behavior with a spectral property, the effective resistance between two nodes. Okay. Now, if you sum up this effective resistance between all pair of nodes, you get what we call the total effective resistance. This is give you a way to measure potentially how bad this graph might have this over-squashing issue. Okay. And as a practical remedy, if I given a graph which has over-squashing issue, one way to fix this is to add shortcuts. Okay, I want to add shortcuts to minimize the total effective resistance. Okay, this problem turned out to be NP hard. Okay, a recent paper just appeared in arXiv shows that we provided a greedy approach, but I think algorithmic perspective, what is approximation algorithm with a polynomial time approximation algorithm to find the best k edges to reduce the total effective resistance. This is still open. It's a very interesting question. Okay. All right. Let me just point out that since I mentioned the shortcuts, in general, adding shortcuts is one way to help me to make the graph structure nicer and to solve a lot of this over-smoothing and the over-squashing problem. But you can add shortcuts, the extra edges, to make the graph look nicer. But what is that? What are the principled ways to add that make it consistent across different graphs? Okay, and also when you add them, what can you say about these shortcuts? Okay, so these are all open questions. we try to attempt look at this by one specific type of shortcut, which is that given a graph, you just add one virtual node, connect to everybody else. Okay, so this reduces the graph diameter to 2. It's also canonical across different graphs. And of course, I mean, this virtual node can aggregate all the information, but all the information is only aggregated in a very specific way. You can probably do mean subtraction, moment computation, but you cannot directly communicate between two nodes. Okay. Nevertheless, empirically, you see that just adding this virtual node already helps a lot, sometimes beating the transformer performance on the benchmark data sets. Graph transformer performance. And theoretically, you can also show that just adding this virtual node allows you now to approximate linear transformers very efficiently. And you can also approximate the standard general graph transformer with different width and the depth trade-offs. Okay, and I think I really overused my time. Let me just leave this open question slides here. And thanks for your attention.
Thanks, Yusu. One very, very short question. Very, very short. Very short.
Somebody else. I'll ask you.
Oh, sorry. What?
Sorry, will you explain what over-squashing is? It's really like a clarification.
Oh, okay, so over-squashing itself is referring to, because the method passing is very similar to local algorithm. Every time you aggregate information from your neighbors, and then this is memoryless. Next time, when you aggregate information from neighbors, you don't know where those messages are coming from. So essentially, this gives you a computation tree, okay? So if every node has 2 neighbors, this already gives you, your computation tree is already a tree, a binary tree. So the size of this tree grows exponentially, depends on the degree, okay? Since you don't know where the message is coming from, presumably you are supposed to, because you don't know what information is relevant, you have to aggregate all this information into some fixed size features. So that's why it's called over-squashing. Now, different type of graph structure. So for example, you have 2 clicks, but only one edge in between. As you can see, you have a bottleneck edge here. So this edge suffers from over-squashing even more, because all the information between the 2 clicks has to go through this, negative curvature edge. So that's why the graph structure, even though all graphs suffers from this issue, but the structure of the graph, some are worse than others.
Great, thanks.
Thank you. So have you thought of incorporating, for example, fractional random walk there? So then you can jump much higher and then you can, look at farther neighborhoods. Like, so have you looked, how do your results compare with, for example, fractional random walks? And then you can still do all this, feature aggregation.
So in our analysis, we follow one typical type of method passing neural network where you don't jump ahead, but empirically people do. I mean, you have this random walk-based graph neural network which allow you to go a bit further. So in our case, this is compared to the lazy random walk, because we have some probably stay or I move to immediate neighbors.
Yeah. So you do like K-hope neighborhood, like mixed hope. There are a number of papers like a couple of years ago, mixed hope and so on. But that is for integer random walk. So when you have long range dependence, you can actually have fractional Laplacian or whatever you do, and then you'll kind of immediately integrate some of this heterogeneous structure of a graph through this fractional random walk, and then you can combine it with what you're doing.
Right. No, I haven't thought about that.